Welcome to Module 2, Working with Data. This is the lecture for the Introduction to Bioimaging Data, which accompanies the notebook. There are many types of bioimaging data throughout biology, biomedicine, and space biology. I've put just a few examples on the slide here from the Open Science Data Repository from different bioimaging data sets. So for example, from OSD 628, we have microscopy images showing biofilm formation in microgravity. We also have from OSD 595, images of Drosophila or fruit flies in artificial gravity. And on the top right, OSD 120, images of plant growth on the ISS. Then at tissue level from OSD 48, we have microscopy images showing oil red O staining, which shows fatty lipid concentration within the livers of mice that have been flown to space. Or on the bottom right, at the same resolution, we have histology images of those same livers. And then on the bottom in the middle, from OSD 366 and the AWS Open Data Repository, at the cellular level, we can show DNA damage in an individual radiation-exposed cell. So all of these different bioimaging data types can be analyzed using Python and can be used as the input to a machine learning workflow. So in order to work with these types of bioimaging data in Python, there are two very commonly used and powerful Python libraries. The first one is called Pillow. This is a common library for opening, manipulating, and saving images, and can perform many useful and basic image operations, such as cropping, resizing, rotating, etc. Pillow is very flexible and can handle multiple image file formats, including JPEG, PNG, and TIFF. In the notebook, we will be focused only on the TIFF format, but just so you know, Pillow can work with many different image file formats. Matplotlib is a library that is commonly used for creating graphs and plots, but it also can be used for displaying images and overlaying plots on them. So when Matplotlib is used together with Pillow, you can create a complete bioimaging data analysis pipeline. You can do your image reading in and pre-processing using Pillow, and then you can display all of the images using Matplotlib. And so that's how we're going to use both of these libraries in conjunction in the notebook. Here are some examples of functions from Pillow and Matplotlib that enable bioimaging data loading and visualization. So from Pillow, we can import a library called image, and that image library has a function called .open. So this will read in and open an image from an open file path, and we save that image into a variable called img. We can then pass that variable into the matplotlib pyplot imshow function, which will display the opened image to the screen. We can also use this imshow function every time we do an image transformation using Pillow. We can display that transformed image to the screen to see what changes took place. One of the common transformations that we often need to do for machine learning is image resizing. We can do this using the Pillow function resize, where you pass in your desired new width and height of the image. The reason that we might need to do this for machine learning is because it ensures that you can ensure that all images in a data set will have the same dimensions, which is a requirement for certain machine learning algorithms, including neural networks. In other cases, this can also help maintain uniformity in the data set. If you're worried about getting accurate model predictions in a data set that might have much larger images or much smaller images. And it can also help eliminate irrelevant details and noise from images that are larger but don't need to be. However, I say all of this with a note of caution, because if you change a biological image, this resizing change may have a large effect on the biological signal. And we'll look at an example of this in the notebook. So before blindly going ahead and resizing your entire data set to the same size for a machine learning workflow, make sure you understand your data set and what that change is doing to the data and to any biological signal that you're hoping the model will pick up on. Another important step in many machine learning workflows for bioimaging data is normalizing the data. We can do this by converting our image, our opened image from Pillow into a NumPy array, and then normalizing by dividing that image array by the maximum pixel value. And this will normalize the pixel intensity between 0 and 1. This can be very useful for machine learning to ensure that all of the images have similar pixel value ranges, similar to what we saw with the tabular data. It can help machine learning models converge faster during training because they don't have to deal with values that are on all different scales. And it can help the models learn only what the important features are by eliminating variations that may exist in lighting and contrast. And it allows for uniform comparison across different images where images aren't all on different scales. However, once again, I do say this with a note of caution because in many bioimaging applications, unlike other machine learning applications, but specifically in bioimaging, the intensity of the pixels in the image is the important feature for model prediction. And so scaling all of those pixel intensity values to be in the same range is actually losing signal, and it would be inappropriate for many data sets. So once again, before blindly normalizing a bioimaging data set for a machine learning workflow, make sure that you understand your data set and what normalization would be doing to that data set. Finally, another very common aspect of a machine learning workflow for imaging data is image augmentation. And this is a process by which we create new and slightly altered versions of existing images in order to expand our existing data set. One of the main reasons to do this is because this reduces the chance of overfitting. It exposes the machine learning model to more diverse training examples. It can mimic real world scenarios where the data is going to be a lot noisier, and it makes the model focus in only on the important features to distinguish between the different classes. So I put an example of different image augmentations of a picture of a cat, adding brightness, cropping, adding grayscale, etc. There are many common types of image augmentation for machine learning, as shown on the right. We're going to be focused in the notebook on flipping images, cropping images, and rotating them. These are just a few of the things that you can do with a bioimaging data set in order to prepare it for a machine learning workflow. And these are the most common aspects of a machine learning workflow for images. So we will dive deeper into this in the notebook.